So really overwhelming to see everyone here. Thanks everyone coming in person. Just before we start, quickly about me. I'm Michael. I'm a senior product manager here at MongoDB. And I've been at the company for a little over 2 years now. And my main focus is time series and time series data, and particularly around the native support we released in MongoDB 5 and everything we've done since and where we're actually ultimately going. So before I start, just quick show of hands here. How many people have used time series collections in MongoDB since we released them a year ago? OK, a few of you. That's good. All right. Well, great to see. At least you're interested, right? That's what matters. So my presentation today is really going to be focused on how we work with time series data in MongoDB, and really about what we built. And so it's really great that actually a lot of you have not used time series collections before, because a lot of what I'm going to cover is some core fundamentals and go into more of the technical details of what's actually happening under the hood and why you would or maybe want to use time series collections for use case and how it may fit for use cases you have. So launched in MongoDB 5, we introduced the concept of native time series support. And really what this was around is making it faster, easier, and ultimately less expensive to work with time series data in MongoDB. And before we get started, let's just quickly go over some of the terminology and concepts that really help to understand not just what we released and but what time series data ultimately is and what it's all about. So time series data, in its simplest definition form, is a sequence of measurements over a period of time with a common metadata. Forgive my clicker there. And so some use cases for time series, it's IoT, your smartwatch, your phone, fleet monitoring, looking at cryptocurrency prices, stock ticker trades, weather symbols. It really, time series data is everywhere. It'd be hard pressed to find anyone in this room that's not currently emitting time series data with either a smartwatch or a phone or something that they have on them, right? Now, at the core of what we built in MongoDB and how we support working with time series data is the concept of a time series collection. And what a time series collection is it's a collection, just like any other collection, that organizes writes so data from the same source is stored in the same bucket alongside other data points from a similar point in time. Well, that sounds like a mouthful, right? Sounds pretty complicated, and hopefully you take away one thing from this presentation is that it's really not that complicated, and everyone here can understand this no matter how technical they actually are. And so we'll expand upon this definition as we get through the presentation more and more, but the key takeaway from this slide is really the advantages of a time series collection. And what it's really about is increasing developer productivity, reducing complexity for working with time series data, reducing I/O, reducing your storage size and your index size, and really utilizing our wire tagger cache and the underlying fundamentals of MongoDB in an optimized way. So as I mentioned before, time series collections are just like any other collection in MongoDB. Creating them, you can use the same create command, or in this example, the create collection helper available in any of our drivers. And it's really just a new option to that create command of time series. And the only thing that's required is a time field. So to create it, you need to tell us the name of a field in your document that corresponds to a time. There's some other fields here, and this is what we'll go over in the next few slides and we'll ultimately expand upon. And these are really about optimizing performance for time series data, but ultimately your use case too, and making it a solution that's customizable in a lot of ways without having to go into the underpinnings of the actual fundamentals here. And at a really high level, though, a time series collection, while it looks and feels like a regular collection and ultimately behaves in a lot of ways like one, it's really actually a visualization layer for an optimized collection. And that's what we'll talk about here, because storing time series data, simple, right? In MongoDB, we have the document model, store a bunch of documents. Can be problematic, though, and we'll talk a lot about that. So that other field in here in the create collection that's really important for optimizing performance is the metaField, or a piece of metadata. As we said before, time series is really about a sequence of measurements over time identified by a metaField, or a metadata. And so the metafield is a label or tag which uniquely identifies your time series. And what that really means is it never or rarely changes. In this example here on the left-hand side, we have a couple of documents with a sensor ID value. As you can see, we specified in the top-level command that is our piece of metadata. And they have a value, and it's a very simple key-value pair. Now, these are measuring temperature, and so you can think of this as a weather sensor, right? So if I have a weather sensor in my front yard, and I'm not tracking anything or I'm not moving it, the identifying value of this 1, 2, 3, 4, 5, 6, 7, 8, 9 key value pair, it's really not going to change, right? Maybe it will change at some point if I move and I want to change it, but this is really identifying my series for a period of time. So often when creating a time series collection and optimizing for the best performance, choosing your metafield is where you're going to spend at least the most time thinking about what is optimal. Because what you want to realize here is that while this field is anything you want it to be, an array, an object, just as the document model allows you to be, everything you add to make this more complex of a piece of metadata, the higher your cardinality can become. And really, cardinality is the number of unique time series, particularly when you're concurrently inserting them or can possibly concurrently insert them. So if you think of an example here where we make this an object and there's something that's always changing, maybe even it's a small dictionary value that we add to this, there's then 3 extra fields potentially, if there's 3 possible values, along with the sensor ID to uniquely identify this. So now you're expanding your cardinality. And while MongoDB does a really good job at handling high cardinality use cases or allowing you to scale for them, ultimately, you need to identify if your use case is high cardinality, right? There's nothing wrong with putting fields that are changing really as what they are, which is a measurement. And so a measurement is pretty much, in its simplest term, anything aside from the metafield and time field, or a set of related key value pairs at a specific time. In this example here, same example, it's just the temperature value. Now, like the document model in the metafield, this can be just as adaptive as you want it to be. It can be an embedded document, arrays, a bunch of nested values, it doesn't matter. For simplicity and screen real estate, this is just a simple temperature value. There's no restriction here to flattening your data or not working with the normal MongoDB document structure. It's actually, you're going to see better performance as you start to put more measurements in to a certain extent, right? Now, if you want to be flat, you can be flat, but you don't need to be. The next one is one we'll actually touch on a few times in this presentation, and it's the option of granularity. So granularity is a parameter that accepts 3 possible string values of seconds, minutes, and hours. And really what this is about is saying, well, is your use case high frequency or low frequency or maybe somewhere in the middle? But it's not just about your overall ingestion rate like you would think in a regular collection, right? Now, when we expand upon this, you'll see why that's the case. But the easiest way to think about this as a high level is what is your ingestion rate as it relates to your metafield? So if you have 10,000 sensors, and maybe on average, sensor 1, 2, 3 is only inserting data every couple of minutes, but every second you're getting data from sensors. Well, that's actually not a high frequency as it relates to the value options here when it comes to the actual metafield insertion rate. So at a little bit of a deeper level, which we'll expand upon, granularity ultimately controls the span of time in which measurements with the same metafield are stored and grouped together. And last but not least, something that's probably familiar to many of you in the room here, it's the expire after seconds option. And really, what this is it replaces secondary TTL indexes for time series collections. So you don't need to create a secondary index to take advantage of TTL deletion capabilities. You can go ahead and use the callmod command at any point to set or change the expire after seconds parameter, just like you would on a regular TTL index, without the cost of creating an index for it. So you don't need to specify this on creation, but if you do want to delete your data for periods of time, then you can go ahead and use this at any point. So for the next couple of slides, we're going to go a little bit deeper and expand upon all of those definitions and really get to kind of the brass tacks when it comes to working with time series data in a simple way so it's optimized for you and you aren't thinking about how to actually optimize performance after maybe a couple of hours here thinking about this, or hopefully a couple of minutes. So as I mentioned before, time series collections, just like any other collection, at least conceptually, right? They have a materialization layer that ultimately allows you to work and see your data as you insert it. So the simplest way to work with data in MongoDB from a time series perspective is the concept of a document per event, right? So in this example here, I have an insert many statement for a batch of 4 documents here for 2 unique sensor ID values, which was our metadata, and that same structure of just a timestamp and a temperature. And you go ahead and you can write your data like this. And when you go ahead and query your data, you get it back just as you inserted it. Now, many of you have maybe tried to work with this kind of model and time series data or large amounts of data in MongoDB before, or in other systems can see how this is pretty inefficient pretty fast if this was actually how things were done at a deeper level, right? Your index sizes will be extremely large, especially in the case of time series data, which is constantly growing. Your storage size will be bloated, and really, how are you going to read back this data over time, right? It's not going to be efficient. It's a lot of index entries. So what makes time series collections different, right? Well, first, let's start with the concept of the bucket catalog. So, well, what is a bucket, right? Well, a bucket in its simplest term is a group of documents stored together as one document with the same metafield for a time span. So now you could probably start to see, right, how we're connecting the dots on the different parameters here, right? That metafield, well, we're looking at the same metafield, that time span controlled by granularity, and this concept of a bucket are grouping documents together. So while you're inserting a document per event, we're really not storing a document per event. And we'll expand upon that in the next few slides with some more examples. But the bucketing catalog at a high level is responsible for transforming an insert into a time series collection, that materialization layer that you're going to work with, into a more optimized format and an optimized collection that's actually represented on disk. And we call that the bucket collection. And it's going to synchronize and batch concurrent updates to the same bucket, which you'll see in a minute. And it's responsible for that compression layer, right? Compresses data in memory, and it allocates about 2.5% of total physical RAM for the actual bucketing that occurs, which we'll talk about. It's an in-memory process. And you can actually change your physical RAM, right, at any point if you wanted to allocate more space for bucketing. So you could think, well, maybe I have a really high cardinality. I want to put a lot of resources towards bucketing. You can actually just scale your RAM. You don't have to worry about a parameter here. Or you can do things like sharding, which we'll talk about on the side in a few minutes about best practices. But diving deeper into bucketing, or what buckets are, right? This is kind of the core concept of a time series collection, where we derive some of those advantages and those performance optimizations that you saw on that first time series collection slide, and how we actually work with time series data in an efficient way. So same example as before. A sensor ID, metafield, a timestamp, and a temperature, and then a conceptual drawing of a bucket here. So as you can see, that metafield sensor ID is stored as a top-level piece of metadata, and there's columns underneath it that store the actual timestamps and temperature, right? So time series collections actually use a columnar storage format. While we're calling that bucketing, it's really a form of a columnar storage. And it allows us basically to store like documents together in these buckets, reducing the amount of data we store by grouping them together, and reducing the index size at the same time, reducing your I/O, among many other things. So let's take this a bit further than the conceptual level and look again at that same insert many statement, but broken down for just the sensor ID where the value is 456. So looking at JSON here, we can see that these two documents, while inserted, get stored into this on the right-hand side here. And so the first thing that's noticeable is this metaField, or meta that it's pointing to, is only storing that 456 value once. So automatic, there's a deduplication level happening at the bucket. We're not storing sensor ID equals over and over again, despite how many documents you may have in a single batch or really over time. We're going to be storing those and grouping them together. And it's almost like an easy way to think of it is like a partition key, right? It's like a top-level key for the bucket. And the other piece of the bucketing here is that time span controlled by granularity. Now, what we're looking at here on the right isn't exactly pretty or easy to work with, right? Especially when you start to think about time series data needs to be compressed. You want to really store this optimally. So part of what we want to do here, and one of the it's really the biggest part in the user experience side of this, right? Why should you have to model something like this or work with something like this when it's so much more easy to work conceptually with something on the left, right? So as I mentioned before, I wanted to touch back on granularity. It is an important parameter, that to really think about. While it's still optional, like the metaField, you really should think about, what your use case is here and how you're going to set this and what makes sense. And while we do allow the modification of this field, it starts with the seconds level as a default, and it can only be modified, to be more coarse. So you can only go from seconds to minutes to hours. You cannot go back. So seconds generally is going to be where a lot of users fall, right? That IoT use case, you're inserting in milliseconds or seconds. But we do see, minutes for things like fleet monitoring and other use cases, right? Or, kind of the classic example I like to use for hours is your bank statement. Maybe your metaField is a customer ID, and you're, looking at debit card transactions. Well, how often do you really use your debit card from a personal perspective, right? Maybe business accounts are obviously using their card a lot more. They're generating a lot more data, but it's really the concept of, a lower frequency time series. And so, as we said before, it controls the time span for which measurements, are grouped together. So now that we know a little bit more about bucketing, expanding this definition, it's really about granularity is controlling the bucket time span in which measurements with the same metaField can be stored and grouped together as a single document. And so that time span value that corresponds to the string values that you're going to actually put in here as the collection option. On the second high frequency side is, the minimum time of a bucket is 1 minute and the maximum time is 1 hour. So for a period of 1 hour, we can basically accept inserts or writes from the same source, the same metaField, and put them into one document. And, maybe that is, for your use case, it's very high frequency, but you can set it in minutes case, and we can actually keep a bucket open in memory for a full day. So this allows you to actually, store more data in a bucket. And ultimately, that's what it's about, right? We want to reduce the amount of time series data we actually store, so we can then provide you with all of the efficiencies that you're looking for when working with your time series data, such as low cost, easier to use, faster queries, reduced I/O, reduced resource management, right? And so ultimately, that's why granularity is so important, is because we want to fill these buckets as full as possible. And in our case, a bucket can be filled when time moves forward, say it passes this period, or it reaches 1,000 documents, or an internal limit of 16 megabytes, which is the general document limit and size for BSON. So that's back to the data modeling piece right here, where you're thinking about choosing a metaField, you're thinking about choosing your granularity, and what your data model looks like. And so while I said, you can make your document as complex as possible, the larger you make your documents, really you're actually not getting the efficiencies you think you might be getting by putting everything into one, right? So maybe a flatter structure is actually correct. And maybe some of you, are more used to using, especially for time series data, relational databases. So there's hopefully a less barrier of entry here to some of these use cases that you're using other systems for. So you don't need to do this crazy amount of data modeling to think about how do I fit this all into one, right? So going back to that same example with the sensor ID 456, just as we've seen on the JSON visualization of a bucket here, these two documents are grouped together. Now, when it comes to the time span, what we're really looking at here is these timestamp values. So the span of the bucket is represented as the min and the max values, as you can see in this control field. And this control field stores, the min and the max of other things too, right? If you can think this document has more things than temperature, maybe wind pressure, precipitation, whatever it may be, it'll store the min and the max values. So many of you in the room who have worked probably in the analytics space or with time series data, thinking this kind of looks a little bit like a cube. And conceptually, that's really what it is, right? It's storing a summary level at the top, right? And the interesting thing to note here is that the first insert of the sensor ID 456 is for the timestamp of 9:05. And if you look at the JSON document, the min time actually does not correspond to 9:05. It actually corresponds to 9 o'clock. Now, the reason for this is because in that first example, when we created this collection, we set the granularity to minutes. And so the one thing that granularity also controls is the ability to more naturally handle, without issuing an update, some late arriving data, which is pretty common in an IoT scenario. So while we'll talk about a little bit about best practices, your data should come in ordered, hopefully, or at least in some semblance of order. It's possible to have cases where you need to backfill data. Data comes in late, whatever it may be. And so granularity helps handle those cases that may exist naturally and maybe are even unbeknownst to you, right? If you don't have control over the data that's being emitted from sensors and you're just simply streaming it in, right? So this basically allows us to say the minimum time is 9 o'clock, even though the first insert that qualified to create this bucket is 9:05. So maybe the next batch comes in and sensor ID 456 has a measurement and or a document that has a 9:03 timestamp. Well, it'll get actually placed in the same bucket here. And just looking quickly at the rest of the bucket here, as you can see on the bottom, there's a data object, and this basically is references to the rest of the data in the document. So these are those column values basically in JSON. So the next thing I want to talk about is indexing on time series collections. And I think that that'll help really expand upon how to optimize or how we're actually optimizing for you in a natural way. So time series collections index just like regular collections from a user standpoint, right? So you issue a create index command, however you want to create an index, a secondary index, a compound index, index a nested field. That's all of the same language. There's nothing you need to think about on how we're storing this data. You don't need to think about how the bucket is structured or how anything like that is. But what it actually means is, for a time series collections, when we take these indexes and we see them being created, we translate them to that buckets collection, just like we do your inserts and your read queries. And the indexes actually point to a block of data or a bucket, right? And those buckets are those groups of documents. So when we index buckets. We don't index individual documents. And this results in hundreds of times savings when it comes to index sizes on regular collections. Even some of you may be familiar with the concept of trying to do a bucketing pattern in other systems, or even manually within MongoDB prior to MongoDB 5. And a lot of that, you are getting some of the storage benefits by doing that, and some of the read benefits. But when you index, that's where things start to break down, right? Because now you potentially have large multi-key indexes of array values. And then you're looking at things that are just potentially even larger than the bucket themselves, right? And that's no good. So we wanted to avoid that. And the other thing to note about indexes here is that we actually create a clustered index. And so a clustered index simply means the data is ordered on disk, right? And in the case of a time series collection, our clustered index is on time. And that time corresponds to the bucket time. So each bucket, as we said, has that min time. that minimum time, which is a little bit like before your first insert for a bucket, and we will actually create that automatic clustered index on them, so all of our buckets are ordered on disk. And this is about really reducing the cost of scans, being able to leverage this without a secondary index for things like sort operations, and ultimately it also allows us to store adjacent buckets in the same data page, right? So faster access to data on disk. So back to the same insert statement, looking at just the sensor ID 456 values here. The clustered index on time. Here is that bucket min time, which actually corresponds to the only field in this that we haven't touched on, the underscore ID value. So unlike an underscore ID in your documents, this is the primary key of a bucket collection. So the primary key is a system-generated clustered index, which corresponds to underscore ID, and the time aspect is equal to the minimum time, which is available in the first few bytes of any object ID in MongoDB, right? So this is guaranteed to be unique, and it's guaranteed to have that timestamp stored in order on disk. So let's walk through some examples of creating secondary indexes. So as I said, same command, create index. Let's create it on the sensor ID here, that metaField, right? So what this actually means is that a single field index of meta is created on that bucket level. So you're indexing a group of documents instead of the individual documents, right? So for those two documents, there's one index. Now, what about a compound index? So let's create a compound index on the sensor ID and the timestamp here. So a compound index is created for you on the meta, just like the sensor ID before, and also on the min and the max timestamp of the bucket in that control field. So this is how we start to take advantage of some of those like summary level information, some of the cube functionality, right, where we're looking at basically not individual index entries or individual document values. We're looking at what composes an individual document on disk to us, which is really a group of documents stored together. And announced today with MongoDB 6.0, we've released the ability to create secondary indexes on measurements, which just any other value in your document. So now reduces that limitation that we released with last year and allows you to just freely index any fields here. So in this example, creating an index on temperature. Just like a timestamp, creates a compound index on the min and the max values of a bucket up at that control level. Well, now that we've created some indexes, how can queries actually use them? Or how do we actually return those individual documents for you when we're dealing with these buckets in an efficient manner? So at a very high level, when you're querying a time series collection for the simple find command or any other aggregation, there's two main things that happen under the hood. The first is the concept of query rewrites, and the second is bucket unpacking. So first, talking about bucket unpacking, this is really about, just like when you issue a write statement, we go ahead and we actually look at the bucket documents. We look at the bucket collection. We index on the bucket level. So we need to provide you, though, with what you inserted. It wouldn't be any helpful to you if we gave you back a bucket, just because we stored it on purpose in that way, and we were getting storage efficiency and query efficiency. If we gave it back to you, what usefulness is that, right? So we need to get it back into the form. And this is simply just going to go ahead and unpack these buckets, or if you're familiar with the $unwind operation, very similar. It's going to go ahead and take the bucket, and it's going to return your documents back as you would, and you don't need to know about it. As we talked about, the query rewrites are really about issuing operations on the bucket collection as you issue them on this materialization layer we provide. And so how they use indexes, though, is really about using those min and the max values and the metaField, and limiting the amount of buckets we return for processing, right? So we want to avoid unpacking as many documents as possible. Sure, we can, and we will, if you issue just a simple find, like in the example. But what we want to gain efficiency from is by actually utilizing these secondary indexes and utilizing this control object here. So for this example here, we have a sensor ID and a timestamp is greater than or equal to. And we'll go ahead and actually look at all of the buckets and say, OK, which buckets ultimately qualify to fit in this range, right? So while the sensor ID equals 456 is very simple, straightforward, it's a point query, right? We can look and see which buckets have meta 456. Time series, though, generally not issuing the most point queries or have the ability to really go ahead and say, I'm filtering on a specific value. You're looking at ranges, right? Your time ranges. You're looking at different ranges of values, or you're looking at all values over ranges, right? Your group key ultimately a lot of times is going to be time. You're going to sort by time, so on and so forth. So this then goes and looks at this timestamp greater than, and we say, OK, which buckets actually have some measurements that may or may not, or that may qualify for this. So we can automatically eliminate buckets, and we use these index entries to say these buckets don't qualify, don't send them to the unpacker, right, which is the internal stage for the unpacking. So we're reducing the amount of data we're processing and ultimately having to return. So best practices. Time series collections, as I mentioned before, are a columnar storage format. With any other columnar database or columnar format, they're not really built to maximize write throughput. Now, while time series collections can keep up with your data, they can write very well. If you're really looking to have a write-heavy use case for time series data, which does exist, right? Maybe you don't have your typical read requirements of low latency, but you have very high write requirements. You need to capture all of your data as quickly as possible. And so to maximize write throughput, you can disable retriable writes. Retriable writes are an automatically enabled feature on the driver. There's a setting on the drivers, or when you connect to your Atlas cluster, it's already there as enabled as true. And really, this is, if you disable this, it's going to reduce your network round trips. Ultimately going to give us the most performance. It's going to reduce the amount of oplog entries we generate. It's going to really just handle that really high write use case. And ultimately, batching writes, as you showed before, the insert many statement. And you can gain even more efficiency if your batches contain multiple documents per series. So in that example, I had sensor ID 456, 789, 456, 789. There was a commonality in the batch, right? So the great thing about time series collections is that when we see a commonality in the batch, that bucketing catalog is actually taking those inserts, right, and matching like documents to group them together. So when we see a write for 456, we can actually group all of those writes in that batch, the sensor ID 456 or the metafield matches, into one. So for the cost of one write, you're going to get all of those inserts in that batch for that where the matching value. Now, this isn't always possible, but if it is possible, this is really going to be able to gain a lot of efficiency here. And as we talked about, choosing a metafield is really important. A timestamp, bad metafield. Sensor ID, key value pair, smaller things that never really get changed, really what identifies your series. And as we mentioned before, the bucketing catalog, it happens in memory, right? So if you have high cardinality or you want to allocate more to bucketing for your time series use case, which may be really demanding, you can allocate more physical RAM for the bucketing catalog to ultimately be more efficient and keep more open buckets in memory and compress more of your data, right? Additionally, if you want to go with sharding, you can think about an easy shard key choice, which I think is the next session after this, how to choose a shard key, that a metafield can be a great shard key choice for high cardinality use cases because we can allocate all of the hash metafields with like values to individual nodes, and we can really scale out your cardinality use case there. And create secondary indexes, right? So while we create an index on time on the bucket time, we're still going to utilize secondary indexes as we showed. So I am getting we're out of time, but from a release standpoint, as you can see, I'm not going to read all of this. We've done a lot over the last year since the initial release, and this is really just the tip of the iceberg. Time series data in MongoDB and time series collections really are about a collection within your same database that can replace standalone time series databases or the need to really optimize individual performance for time series data. Sure, the characteristics of time series data are different, but it's still data. You still want to store it. You still want to use it efficiently, right? Why think about it? One thing I did want to touch on just quickly is MongoDB, one of the coolest features, my favorite feature, is the concept of columnar compression. Many of you are probably familiar with very common compression encoding or compression algorithms. So with MongoDB 5.2, we released columnar compression, which basically goes and adds a bunch of innovative things as it relates to BSON documents and the document model. So we can compress objects. We can use delta encoding, delta-delta, simple 8B, run length encoding, zigzag, gorilla. All of these things you may have heard of or other systems use, we're able to then actually use them on the document model and reduce your storage and index sizes even further and actually increase cache efficiency by up to 30x compared to regular collections. So you can fit a lot more data in memory when it comes to a time series collection. You can issue a lot of less queries to disk and I/O. And an example of that here is common tick data, so some stock ticker data here, uncompressed 827 megabytes. In memory, with columnar compression, reduced to 55 megabytes. And on disk, when we apply the wire tag or block compression, reduced even further to 34 for a savings on disk of 96%. Of course, this is different for everyone. But it's the shape of your data that's going to affect this. And ultimately, we see that in a worst case scenario, in a more demanding scenario, we still see over 70% reduction in space since the introduction of columnar compression. So there's a dedicated time series booth downstairs. I will be around to take questions for anyone here interested to talk a little bit more. And then there's also going to be experts and some of our engineers who actually built a lot of these solutions down at the booth throughout the week as well. But I'll be outside if you want to grab me for any questions.